What's up, everybody? It's Dan from SageMathTutoring.com. My calculus student could use a little help with implicit differentiation. She just sent me sort of like a homework assignment that she has, so I want to take a look at it and do some of the problems. Actually, I'm going to do all of them while explaining the process of implicit differentiation. However, before I dive into the actual homework, I think it's a good idea to give, again, something of an overview of implicit differentiation and how it, of course, differs from like regular differentiation. So here's an example of really just a regular differentiation problem that features the power rule. So my student is used to being like, okay, if I want to do the derivative of this thing, that's really the derivative of y. And one way of, providing notation is to have this y prime. And the y prime denotes the derivative of y. And then you would just go ahead and do the power rule. So this becomes 6x plus 1. All right, so my student is definitely aware of how to do that. But I think I want to just draw attention to the notation. There is this y prime. That's common notation that mathematicians will use when doing differentiation. Often you might have an equation that is in this like function form as well, where it's like maybe, I don't know, x plus 2 times x minus 3. And we might want to do the derivative of that as well. Now, there's a couple ways of doing it. I mean, you could use the product rule if need be, but you could also FOIL this. So this ends up becoming x squared. I know it's going to be a negative 6 over here, and then I have the negative x. And then the derivative would be this. All right, notice once again the prime, the usage of the prime. And in this case, it would be 2x minus 1. All right, so it's important to understand how to do all of this, of course, and what notation you are using when you're doing the derivatives. Now, it's not always the case, but it is often the case that another notation comes into play only when the class moves into implicit differentiation. I had a teacher who actually provided this special notation long before we got into implicit differentiation, but some teachers will only introduce this notation when you actually get into implicit differentiation. And what do I mean by that? Well, I mean the following. Another way of denoting the fact that you are doing a derivative is to use this dy dx notation. All right. And the way that this could be read is you could say, well, it's the derivative of y, but really what it is the derivative of y with respect to x. All right. The derivative of y with respect to x. Now, again, in the past, we have used notation that says like, y prime equals 18x squared. Well, keep in mind, we still did the derivative of y, right? Y equals 6x cubed. And we did the derivative of it. We did the derivative of y, right? Well, it's really the same thing. It's the derivative of y, but with this extra, verbiage that says with respect to x. The top numerator tells you what you are deriving, and the bottom denominator tells you which variable you're respecting. That new notation will really come into play when you're doing implicit differentiation. Now, the question is, why and when would we want to do implicit differentiation? Well, it's when you're not able to solve for y in the original equation. So, for example, imagine we had something like this. Well, this is something where you can solve for y, clearly, and then you could easily just do the derivative of that in the previously mentioned ways. However, something like the following, imagine you had like x squared plus 3xy minus 2y squared equals -4. Imagine you had something like that. That right there would be problematic because I'll trust my student to recognize that, any attempt to isolate y on the left-hand side and solve for y would be thwarted, namely because there is this exponent of 2 hovering above this y, and there's an exponent of 1 hovering above this y. There's nothing you can do with that. You can't factor out a y and then solve for y because there'd be a y in the thing that you factored, if that makes sense. In fact, let's explore it a little bit. So imagine we rewrite this as this after subtracting x squared from both sides. Let's just take a look at what happens when you try to factor out y. You end up with, this. Right? And unfortunately, that really doesn't get us closer to solving for y, because even if we divided both sides by this thing, we'd still have a y underneath, right? So that's a problem. So the question is, seeing as how we can't solve for y in that green equation, what can we do to find the derivative of this whole thing? Well, let's say the teacher says, please find the derivative of y with respect to x, okay? Please find, in other words, dy dx. What does that equal? Well, here's the game plan. I'll just kind of tell you right now, my student who is watching, the game plan is as follows. You essentially take the derivative of freaking everything that you see. Okay, you take the derivative of this, you take the derivative of this, this, and that. Okay, you take the derivative of everything. But here's the deal. We're taking the derivative of y with respect to x. So what that means is we're going to quote-unquote respect x. Here's a way of thinking about it for my student. What this means is we are not going to rough up the x variables. But what we are going to do is rough up the y variables. And what I mean by rough up the y variable, what I mean is we're going to do the chain rule like crazy on the y variable. The chain rule is the ultimate sort of derivative method that sort of roughs up the function, all right? Because think about it. You're taking the derivative of the function, and then you're taking the derivative of the thing that was inside the function. So you're like really roughing it up. So when we take the derivative of y with respect to x, we are respecting x and therefore not roughing up x. But y is getting roughed up. Now, what does that look like in practice? What that looks like in practice is going about, the derivatives just all the way across the line. Let's start with the first term. Clearly that becomes 2x. Notice how I'm just leaving it, right? We are respecting x. That is just a normal scenario. But then we have this other scenario coming up soon that says plus 3. Now we're going to have to do the product rule, so I'm just going to do this right now. And it's going to be 3 times the product rule. All right. So that's going to be 3 times the derivative of x, also known as 1 times y. And then we do x times the derivative of y. Now, what is the derivative of y? The derivative of y is dy dx. That is literally the derivative of y with respect to x. All right, so this was not much of a chain rule scenario. There wasn't much we could do. The derivative of y is simply dy over dx. And then we're going to move on to the next thing, where it's going to be power rule scenario over here. That's going to be negative 4y. But now we do the chain rule to this y. And as we already said, we know that the derivative of that is dy over dx. And then it still equals -4. So we can't forget that. Try not to forget that. -4 just turns into a 0. And then at this point, let's distribute the 3 in there. So we end up with, I'll do a different color. We end up with 2x plus 3y plus 3x dy over dx. Let's see, minus 4y dy over dx, and that equals 0. All right, so hopefully that is clear so far. Now what you want to do here, this is always the case actually with implicit differentiation, is you take note of the terms that have the dy and dx in it. Dy over dx, that's right here, and that's right here, and you're going to want to isolate those first. Now how can we isolate this term and this term? Well, we'd have to subtract away 2x and 3y, and I trust my student knows how to do that. This would be 3x times dy over dx minus 4y dy over dx, but we would have negative 2x over here and negative 3y over here. Then the reason for isolating these two terms is the fact that now we can factor out the dy over dx. So we have dy over dx factored out, and we have 3x minus 4y inside the parentheses. We still have this negative 2x minus 3y over here. So then what do we do? Well, we want to figure out, what dy over dx is, right? That was the original mission. Well, we're perfectly poised to do that by dividing both sides by this 3x minus 4y. So after dividing both sides by that, we end up with dy over dx equals negative 2x minus 3y all over 3x minus 4y. Now, that is really the answer right here. I would caution you, occasionally the back of the book might represent the final answer as the following. The book, textbook might represent the answer as 2x plus 3y all over 3x minus 4y with this negative in front. All right, when the negative is placed in front of the bar, what that means is this negative could hypothetically be applied to the entire top, or the negative could be hypothetically applied to the entire bottom, okay? But not both. The negative either goes here or it goes there, but some mathematicians like to just keep it off to the side perfectly. All right, now if we're going to do it that way, then we'd have to make this 2x plus 3y. All right, so that is how to do implicit differentiation. Now at this point, we're going to jump into my student's actual homework assignment, and we're going to see what we can do. Okay, so I can already see that this is the homework assignment from hell. Not only because there's implicit differentiation, which is perhaps inherently annoying, but also because we have, the derivatives of all kinds of annoying things like arctans and what have you. But nonetheless, we're going to forge ahead and destroy this homework assignment. So let's look at number one. Number one, it says find dy over dx by implicit differentiation. Y equals 3 cosine x sine y equals 1. All right, so, good idea to just sort of write it down. So we have 3 cosine x times sine y equals 1. And then what did I say before? Well, you do the derivative of literally both sides of the equation. So we could see very easily this is going to be a product rule because the whole function called cosine x is being multiplied times another whole function called sine y. So we are going to write the 3. I'm comfortable with brackets, to be honest, and parentheses, because that 3 we need to remember is going to be applied to the whole thing. Now while I'm here, I might as well just do this. 1 becomes 0. All right, so this one right here becomes 0. Let's just get that over with. Okay, now we're going to have to go into this quagmire right here. What I'll do is, the derivative of cosine first. I mean, whatever. It really doesn't matter with the product rule which derivative you do first. So we are going to go ahead and simply do the derivative of cosine first. Now, as my student knows, that is definitely negative sine x. Now, we are respecting x, so that's as far as we're going to take it. This sine y just simply remains sine y. Okay. Now, we're going to keep the first function, call it cosine x, and now we're going to do the derivative of sine y. Now, the derivative of sine y is cosine y, but unfortunately, it's going to be cosine y, sure, cosine y, but we're doing the chain rule, right? So we have to do also the derivative of this thing, also known as dy dx. Okay? So that is unfortunately what we sort of have to do for that problem right there. And let's see what happens. So we could always distribute that 3, and that would become negative 3 sine x sine y plus 3 times cosine x cosine y times dy over dx equals 0. Now, mental note, sine x and sine y, I can't just call this like a sine squared something because the actual angles that are being signed right now are different. All right, same with the cosine. All right. Either way, this is the term that features the dy dx in it, so we're going to isolate that, and we're going to do so by adding the negative 3 sine x sine y to both sides. And once we do that, we have this 3 cosine x cosine y dy over dx, and that's going to equal 3 sine x sine y. And finally, what I refer to as the kill shot, which is to isolate dy over dx. We're going to do that by dividing both sides by this 3 cosine, x cosine y. And after dividing, we end up with dy over dx equals 3 sine x sine y all over 3 cosine x cosine y. And at that point, the teacher would most definitely appreciate canceling the 3's out. And, I'll actually just sort of, to save room, I'll just like erase them at this point. All right, I'm going to trust my student doesn't get confused by that move. All right, we cancel those out, no big deal. And at the end of the day, really, this is the answer. Okay, so that's how you do that one. All right, looking at number 2. Find dy over dx by implicit differentiation. We've got x to the 4th, y to the 3rd equals 1. All right, so at least at first glance, this one looks fairly easy. I don't want to get too cocky. We've got x to the 4th plus y to the 3rd equals 1. Treating x as normal, we end up with 4x to the 3rd. And then we're going to have to rough up this y. So it's going to be plus 3y squared. But we're not done yet. That is going to be also the derivative of y itself, which is dy over dx. And that will equal 0. So be sure to do the derivative of this side. Some students will forget that. Some students, they're so used to doing the derivative only of one side that they completely forget to do the other side. So don't forget to do the other side. At this point, this is the term that has the dy over dx in it. So we're going to isolate it. After subtracting 4x to the 3rd from both sides, we end up with this. And very, very easy from there, just divide both sides by 3y squared, and we would end up with negative, I'll stick the negative in front of the bar, negative 4x cubed all over 3y squared. That, unless I made a careless mistake, which is always possible with these videos, that's the answer. All right, looking at number 3, looks a little bit more tricky. That's once again dy over dx, so I'll write number 3 down. Number 3 says x squared y squared plus x sine y equals 2. All right. Okay, so already I'm seeing probably going to have to do the product rule here, and unfortunately we're going to have to do it here too, because it's a product right there, right? So let's kind of get ready for that adventure. My student knows me by now. I definitely like to begin with the end in mind, which means begin with parentheses, because I know I'm going to be doing that anyway. And then over here, let's, get ready for this product rule. All right. Maybe it's just like the part of me that likes to be super organized, all right, which I feel like as I get older, I see the value in organization more and more. So let's see, x squared, y squared, we are going to, for now, we'll keep the first one, change the second one. We'll just stick with that pattern. So keeping the first one and changing the second one. That might be the opposite of what we did last time, but whatever. Finding the derivative of y squared, well, that's going to be 2. It's going to be 2y. And by now, I hope my student is getting the hang of it. That will be dy over dx. And now we're going to do the derivative of the first thing, which is going to be 2x, and we're going to keep the second thing. Easy peasy. Now, over here, we're going to stick with the pattern of keeping the first thing and find the derivative of the second thing. That ends up becoming cosine y dy over dx. Thank God for the zoom in feature. And then we're going to take the derivative of the first thing and keep the second thing. All right, my student and I have done enough calculus together where I am confident she knows what I'm talking about there. For those of you who are not my student watching at home, you might be a little lost, and I apologize for that. This is not really a calculus tutorial designed to help you from square one. For those of you who sort of know the basic rules already, this might be helpful. So anyway, we got the string of a whole bunch of stuff, keeping the first thing, change the second thing, derivative of the first thing, keep the second thing, keep the first thing, change the second thing, derivative of the first thing, keep the second thing. And then we could just simplify where we could. I don't know, we got x squared, 2y. This, even though there's parentheses, this is kind of what the term would look like. This is kind of what this term would look like. This is kind of what this term would look like as well. And this would just be a sine y. Let's just keep that in mind. Since there would be no real simplification on the next line, I'm going to just leave it at this. But we are still nonetheless going to take note of where does dy over dx occur. That's here and that's here. So this term right here and this term right here, these guys get to stay, whereas this one and this one have to go. So on the next line, I'm going to write the terms that get to stay. I'll stick this 2 out front. That's something you should definitely do. And we end up with this on the left. And on the right, we end up with, it looks like, negative 2x y squared minus sine y. And then at that point, it's now time to factor out the dy over dx. And when I do so, I end up with 2x squared plus x times cosine y, and that equals negative 2xy squared minus sine y. And then, of course, we're going to divide both sides by this thing. And we end up with, as a result, dy over dx equals what looks like it's going to be. And I'm just going to get this over with. The negative is going to go in front of the bar. So we're going to have 2xy squared plus sine y up top. And we're going to have 2x squared plus x cosine y down below. And that should be the answer. Okay, so that was number 3. Looking at number 4. So find the derivative of the function arctan. Okay, well, I stand corrected. This is not implicit differentiation. I thought the whole thing would be implicit differentiation. This is not implicit differentiation, but rather this is just, the derivative of arctan. That is something that you should memorize, okay? Most teachers will provide their students a reference guide when it comes to all these sort of famous derivatives. And I'll just denote to you guys what the derivative of arctan is right now. So the derivative of arctan could be denoted like this, where it's like the derivative of arctan x. Okay, that's one way of saying it. Maybe I could sort of clean it up by putting this dx like kind of underneath in a centered way. Now, this equals something. I'm going to tell you what that is, but let's get clear on the notation. This d is like the derivative of this with respect to x. All right, so for my student at home, this used to be the derivative of y with respect to x. Well, now it's the derivative of arctan with respect to x. All right, so that's one way of saying it. And it so happens that if it's just an x, arctan x, if it's just that, then the derivative is going to be 1 over 1 plus x squared. Okay, so that is key to our understanding. That's key to our understanding. So let's move this up here. In fact, it's so key that we're going to leave this here as a reference. Now, we are going to embark on our journey of finding the derivative of arctan radical blah, 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 blah. Now, that is a tricky situation. It certainly looks like it's going to be a chain rule, right? Certainly looks like that because it's the arctan not of x, but of a ridiculous mutant version of x. All right, so let's go in there. So we have y equals arctan of this ridiculous thing. My handwriting's not the best, but I think you probably get it. We have 1 plus x. Okay. So when you're doing the chain rule, you just proceed as normal. Okay, you proceed as though nothing unusual is happening. And you just, do the derivative of the thing, right? So the derivative of arctan is, well, it's going to be 1 over 1 plus, now here's where you got to be careful, it's going to be something squared, but the thing that goes here is whatever is being arctanned, right? This was arctan x, right? So the thing that's being squared down here is x. We're squaring whatever the angle was. Or what is it? Maybe that's actually not an angle. That is a measure. All right. So we're going to have to fill this in with this whole thing. All right. So here we go. And then you just pause, take a deep breath, okay? You might be able to see that, okay, we could square this and get rid of the radical, but I'm not even going to go there yet. Because at the end of the day, we're doing the chain rule. And the chain rule says that you can't just stop there. You now have to multiply this whole thing, like literally the whole thing, by the derivative of this function. So we're going to have to find the derivative of this function, and we're going to put it in here. So the question is, what is the derivative of this debacle? Well, that is absolutely a perfect time to set aside this original problem and go off to the side and treat this like a separate issue. All right, I'm just going to call it G. G is equal to this. So now what we want is the derivative of G. But here's the friggin' problem. We're going to have to do the chain rule to this thing. Okay? I know it's freaking crazy, but we're actually going to have to do the chain rule to this thing. And the reason is because at the end of the day, this G is really a mutant version of what would otherwise be a normal situation. Because G equals the square root of something. Well, this G equals the square root of something. Well, what would you do in this case? You would, call it x to the 1/2, and then doing the derivative, you would end up with 1/2 x to the negative 1/2, which would end up being 1/2 radical x. Now, I think it's helpful to know that g of radical x, when you do the derivative, would turn into this. All right? That's important because we're going to sort of apply that wisdom right here. So let's do it. We have g prime equals what? Well, according to, what we just discovered, it's going to be 2 times, radical whatever was underneath the radical. What was underneath the radical here was x. Well, that's what goes down here, right? So this is going to be 1 minus x all over 1 plus x. All right. Once again, when you had g of radical x, it turned into this. So you end up with this down below. Well, same thing with this. G prime equals 1/2 times radical this thing. But we are not done because we're going to have to do the chain rule to this guy by multiplying this whole thing by the derivative of what's underneath the radical. So clearly this is sort of a mess, right? But you have to stay calm and do things one thing at a time, and maybe even use dividers when need be. I'm going to call h 1 minus x all over 1 plus x because we need to find the derivative of that now, right? So that is straight up quotient rule, no question. So h prime is going to be something squared with the numerator being thus. All right, and let's zoom in. So what is it that's being squared? Clearly 1 plus x. That goes here. And then we have to put in the derivative of the top. The derivative of the top ends up being -1. And then you take the derivative of the bottom down here, which is a +1, and multiply it by the normal top, which is 1 minus x. Okay, so on the next line, we could say h prime therefore equals the -1 times 1 plus x is, I'll just write it like this, -x minus 1, and then it's going to be minus whatever happens in the brackets. Let's figure that part out right now. That's going to be inside the brackets and ends up just becoming 1 minus x. Okay, so let's preserve the bottom for now. We have 1 plus x down there. And I like to do things one step at a time. There's a huge danger in like trying to do too much in your head. So don't try to do too much in your head. That's h prime, by the way. We have -x minus 1 minus another 1 plus x, and that's all over 1 plus x squared. I do believe my student said that her teacher does not mind leaving the 1 plus x squared in the bottom. Different teachers are kind of different when it comes to that, but we're going to leave it. So we have h prime equals Looks like the x's cancel. We have negative 2 all over this. Okay, 1 plus x squared. So that right here, negative 2 over blah, is the derivative of 1 minus x over 1 plus x. And the derivative of this belongs right here, as you may recall. So we're going to take this guy, and we're going to put it right there. And I'm going to keep it, actually, we're going to keep it in green to sort of get some uniformity. Negative 2 over 1 plus x squared. Okay. Now, simplifying this. Let's simplify it right now. And let's get rid of these guys in order to do that simplification. So let's take a look at this scenario. I mean, it's really a fraction times another fraction. So, I could be like equals negative 2. Let's have a negative 2 up top. Well, whatever. Let's stick with the negative fraction. So we're going to have a 2 up top. And we also have a 2 down below. So I certainly foresee a cancellation on the horizon. And then I have 1 minus x, and I have 1 plus x. And this is 1 plus x squared. I'm going to leave it like that except for the cancellation. So that becomes a 1, and of course that becomes a 1. And the entire purpose of figuring out the derivative of g was so that we could multiply that derivative right here times this. So in a way, we're kind of working backwards, where now we have the derivative, and I'll write it in a way that looks nice. So it's really negative 1 over, this. And you may notice for my student at home that I'm constantly kind of correcting this by dropping this down, because I want to make it very clear to myself that it's the whole thing being square rooted. All right, so all we have to do is transfer this here, right? So that's what I'm going to do. The negative will remain in front of the bar, and then we have this radical and a squared shenanigans. What was it? 1 minus x, 1 plus x, and then 1 plus x. Now, for the record, also, I want my student to recognize that, if there wasn't like a radical symbol here, there would be an opportunity to cancel the 1 plus x with this 1 plus x. But the radical symbol, in a sense, prevents us from messing with this 1 plus x. All right, so just to keep that in mind. Now, I do believe that it would be nice, certainly, to simplify this whole thing. So let's think a little bit before we dive in, okay? First of all, I can already see that the negative could go out front. I could also see that the 1 times 1 is just going to be a 1, so we're going to have a 1 up top. The thing is, though, I see an opportunity right now to simplify this situation by applying the exponent of 2 to the radical symbol, which would cancel out the radical symbol. It's not much we could do here. This is one big lump of multiplication, certainly. I think it would be helpful for us to recognize that the whole denominator, regardless of, simplifying this, the whole denominator in yellow is going to be multiplied soon by the whole denominator over here. I'm going to continue to use the yellow brackets to keep that compartmentalization on the next step. And on the next step, I'm also going to transfer this negative to the front. So on the next step, what we have is negative bar. We definitely have a 1 up top, and we have 2 previously separate denominators being multiplied to each other. And let's go ahead and apply this simplification by saying that this is going to be 1 plus just 1 minus x over 1 plus x. And then over here, we're going to end up with just what it was. All right. Okay. So then you have this term, like this is one term. It looks like a lot, right? But a term is when it's just a lump of multiplication. This is a lump of multiplication. You have some number times another number, right? So we could distribute that, okay? We could distribute that. We could distribute this whole term here, and we could distribute this whole term here. So we are going to do that right now. When we distribute it, we get, I'm going to give myself parentheses with this distribution. Kind of looks like we're doing the power rule, but it's not. It's distribution. It's going to be 1 times this thing and this thing is going to be this distributed here, so that's going to be 1 minus x all over 1 plus x times, once again, I'll refer to this as the debacle. This debacle. All right. Clearly a lot of room for careless mistakes. I hope I'm not making careless mistakes, but nonetheless, if I didn't, the next line should be simply the debacle But what I'm seeing over here is an opportunity to cancel out one of these 1 plus x's and this one. So a nice clean way of representing that cancellation is to cancel this whole thing out, because that thing is going to be gone, and to just cancel out the 2 and replace it with a 1. I'll let my student think about that. She could always pause the video if she has to. So then we end up with plus really 1 minus x. I think it'd be nicer to call it 1 plus x, put that next door, and then we'll end it with this thing. Extend that. So that is one of the ugliest answers I've ever seen in calculus, which makes me a little worried that there might be a careless mistake in there. But assuming the teacher doesn't insist that you FOIL this kind of stuff or this kind of stuff, I think we're good. All right? I think we're good. I'll leave it to my student to consult the answers in the back of the book. If you're watching the video and I made a mistake, feel free to comment below. But I'm pretty sure that's it. All right, so moving on. All right, so the next one is saying, it's number 5. So this one's saying y equals sine, this is really arcsine or inverse sine. It's really arcsine, you know, in the same way that it was arctan before. All right, so as usual, it would be helpful for us to know, okay, well, seeing as how it's like the arcsine of some craziness, well, what's the normal, the so-called normal scenario? The so-called normal scenario would be the arcsine of just x. And if you want the derivative of that, that would end up being the following. That would be 1 over radical 1 minus x squared. All right, so this original function, the arcsine, would turn into that. All right, so guess what? With the chain rule, we are going to begin that process right now. And let's get right to it. It's definitely going to be 1 over radical 1 minus something squared. And what is that something? What belongs here is whatever the mutant is. The mutant is 4x plus 1. I call it the mutant because it's like a mutant version of what used to be x. It used to be arcsine of just x under the normal circumstance. But under the chain rule circumstance, now it's the arcsine of some ridiculous mutant version of x called 4x plus 1. And that's what belongs underneath here. Now, we have to do the additional task with the chain rule of multiplying that times the entire derivative of the mutant itself, and that is 4. This one is just, thank God, much easier than the last one that we just did. 4 is secretly 4 over 1. So this is really just a fraction times a fraction. So you just multiply the numerators straight across. That ends up becoming just 4 up top. And then down below, we have this 1 minus 4x plus 1 squared. Now, you know, again, if we're strictly operating on the philosophy that we're not going to bother foiling stuff in the denominator, you could keep this, but I'm already kind of seeing a potential opportunity to cancel out like this 1. So I'm going to not be a lazy bastard, and I'm going to FOIL that and see what happens. All right, so we're still going to have the 4 up top, and then down below we're going to have 1 minus, and I'm going to put this in brackets because I want to remind myself I am subtracting the whole thing, the whole result of the FOIL. Now the result of the FOIL would be 16x squared plus 8x plus 1. And therefore, we could say that this is 4 over radical, you know, after distributing the negative in there, I'll just kind of stick with the descending order of exponents. After distributing the negative in there, that becomes a negative 16x squared minus 8x. And then, yes, the 1's cancel, right? That cancels with that because it's a positive 1. This negative would distribute, making that a negative 1. So I would wager that unless I made a careless mistake, the answer in the back of the book would probably resemble that. All right, next one says 9 arctan of that. All right, so that's already, I can see this one's going to be just a lot of fun. So y equals 9 arctan of this one. So first of all, let's once again get clear that the derivative of arctan, which is this tan to the negative 1. All right, I'll write it that way. Derivative of arctan is going to be 1 over 1 plus x squared. So we are going to do that to this. It's clearly going to be a chain rule scenario. And let's give ourselves some room here. So on the next line, it's definitely going to be 9 times the whole derivative of all that stuff. Now, the derivative of arctan is 1 over 1 plus x squared, but this is going to be 1 plus something squared, and that something is all of this. And we're just going to pause with that. We also have to remember that this is the chain rule, and now we have to do the derivative of this, right? So we'll get a nice divider. We're going to treat this as a separate problem, and let's call it h. H is x minus radical 1 plus x squared. Now, the derivative of h is going to be 1 minus, the derivative of this, right? But unfortunately, the derivative of this is another chain rule. So this is reminiscent of that thing that we had to deal with before. So we are going to have to say 1 minus the derivative of whatever this is. We're going to leave these open parentheses, and we're going to go on a separate mission to find out what the derivative of radical 1 plus x is. We're going to give ourselves another divider, and we're going to call this next thing g. So g is 1 plus x squared. G prime is going to be the derivative of that. Okay, this might be another chain. This might be another. We might have to do it again. I don't know. Let's see here. Probably not. Imagine you had something called, y equals radical x. Well, we already kind of went over this. We know that this is going to end up being that, right? Well, isn't this really just a version of that? It's radical something. Well, so we know that g prime is going to be this, only instead of x, it's going to be that. So let's go ahead and just write it. It's going to be 1 over 2 radical 1 plus x squared. But we have to be careful because this is a chain rule, because the bottom line is this is not that. This is a mutant inside the radical symbol. This is not. This is a normal x inside the radical symbol. Normal situation. This is a ridiculous mutant underneath the radical symbol. So we have to do the additional step of multiplying this whole thing by the derivative of the mutant itself. And the mutant itself is 1 plus x squared. So we're going to go ahead and multiply the entire thing right here by the derivative of 1 plus x squared, which, thank God, is fairly easy. That's just 2x. 2x is secretly 2x over 1. Therefore, we have a fraction times another fraction. Therefore, this could be said to be 2x all over 2 times radical 1 plus x squared. The 2's would cancel. Therefore, we would have x over radical 1 plus x squared. Now, that's the derivative of g, so we could put that right here in the empty parentheses. Look at that, empty parentheses waiting for us. Guess what? Empty parentheses, well, I didn't draw empty parentheses over here. There's going to be empty parentheses over here, okay? In fact, I will draw them. Here are the empty parentheses that are waiting for us, right there, because we're going to multiply this whole thing by this derivative. So anyway, this belongs here, though, so we're going to put x over 1 plus x squared there. Radical 1 plus x squared. And I feel good about this one. I mean, we could drop the parentheses, but for now I feel good about it. So why the heck did we do that? Well, the reason we did that is so that we could put that lovely derivative. We could put that lovely derivative where it belongs. And where it belongs is multiplied times this, but I'm already seeing that I want this 9 to multiply times the whole thing. So actually I'm going to get rid of this bracket. Alright. And we're going to take that bracket. And we're going to put it over here. Alright. Because again, it's 9 times the whole thing. Because according to the original problem, it's 9 times, the whole thing. So we are sticking with that parameter. And the thing that goes here is 1 minus x all over radical 1 plus x squared. Okay. All right, so yeah, that's hideous. I mean, it's really hideous looking, but at the end of the day, I do believe we are indeed on the right track. Let me think. Yeah, I mean, I think that this term, this is a number that's being multiplied times this whole number. In fact, I'm going to wrap this in parentheses so we're really clear that it's this whole thing multiplied times this whole thing. Now, I know it's a big bunch of gobbledygook, but this is just a number, and you could even say that it secretly has a 1 under it. So you could think of this as the numerator and this is the denominator, where this numerator gets multiplied times the 1, and this little denominator gets multiplied times all that. All right. So a possible final answer is 1 minus x over radical 1 plus x squared, literally all over 1 plus x minus. That is a possibility for sure. And I suppose the teacher might appreciate the 9 getting distributed in. Now, keep in mind, 9 secretly has a 1 underneath it. So you could think of this as a fraction times another fraction. So 1 times the denominator and 9 times the numerator. So we would end up with 9 minus 9x for the same reasons over 1 plus x squared all over 1 plus x minus 1 plus x squared. I hope that that's the answer. Once again, lots of room for careless mistakes there. All right, so find an equation of the tangent line to the asteroid at that. Okay. I'm assuming it's a word problem that features an asteroid. That's sort of irrelevant. At the end of the day, we're just going to have to find the derivative of this thing. And that would, of course, give us the slope. Once we have the slope, it's very easy to figure out the equation of the tangent line. So let's write this down. We've got x to the 2/3 plus y to the 2/3 equals 4. And implicit differentiation would have us call this. All right, and I'm gonna hope that my student understands what's up with that. So we want to isolate the dy over dx. We could subtract 2/3 x to the negative 1/3 from both sides. that would leave this left over. We'd have negative 2/3 x to the negative 1/3 here. And then from there, dividing both sides by 2/3 y to the negative 1/3 would give me this up top. And this down below. Now, let's simplify that. So that would become negative x to the negative 1/3 and y to the negative 1/3. Now, what happened there? Well, I canceled these 2/3 out. There was still the negative left over, though, right? And that negative just went right there. I'm a big fan of not having negative exponents. So I'm going to rewrite this as this. All right, that's an x to the 1/3 down there. Essentially, if you have a negative exponent, you can switch where it is, numerator to denominator, denominator to numerator, and then just change the sign of the exponent. To me, it's a lot easier to think about exponents when they are not negative. We can see that this is the cube root of y, and this is the cube root of x. So this is the derivative of that, right? So we found the derivative, right? Totally found the derivative. However, you know, the derivative could be used to find the slope. Well, how do you find the slope? Well, you find the slope when you plug in the at least one coordinate of the point. Now, we have two coordinates. We have the following point to contend with: 3 radical 3 and 1. And one of the differences between implicit differentiation and regular differentiation is that when you do this, finding the equation of a tangent line stuff, you actually have to plug in both of these numbers. All right. So this is going to be, you know, if I bring it up here, it's going to be something, negative something 1/3, all over something 1/3. Well, the something up top is the y. Well, that's 1. The something on the bottom is the x. Well, that's this. Okay. Now, let's be very clear that radical 3 is secretly 3 to the 1/2. Now, due to my experience, I know that it's going to be helpful to see it that way right now. So I'm actually going to write that as 3 to the 1/2. All right. Now, this is 3 to the 1, and this is 3 to the 1/2. We could simplify this and say, you know, keep the base and then add the exponents. That would become 3 to the 3/2. I foresee that that's going to be useful, to call that 3 to the 3/2. So I'm going to do that right now. We are going to call that 3 to the 3/2. Now, why am I doing all that consolidating here? Well, the reason is because I want to apply this easily and in a way that's not confusing. Now, when you have a power raised to another power, all you have to do is multiply the powers. So on the next line, I'm going to write, you know, still it's like, let's do a different color. Negative, you know, fraction line, you know, 1 to the 1/3, you know, let's just call that 1 because it is. And then we're going to have 3 to the 3/6, right? But what is that? I mean, that's 3 to the 1/2. So this ends up becoming 1 over radical 3. Because this becomes 3 to the 3/6, which is 3 to the 1/2. Anything to the 1/2 is just the square root. So it's just the square root of, 3. I'm going to assume the teacher doesn't mind radicals in the denominator. All right. That would be seen as small potatoes. To rationalize in the denominator would seem like petty small potatoes when you're dealing with all this stuff. But I'll leave it to my students to know whether or not the teacher expects you to rationalize the denominator. Nonetheless, this is the slope of the line in question. All right. And that is hugely helpful because what do we have? We have a slope and we have a point. Easy peasy from there. Most teachers would have you just kind of write the equation like this first, and then you got to find b. Well, how are you going to find b? Well, clearly you find b by replacing y with 1 and replacing x with 3 radical 3 in this case. And then you say plus b, and then we notice that there's a lovely cancellation, and we end up with 1 equals negative 3 plus b, and then b therefore equals 4. And then you take this equation and you rewrite it with your newfound knowledge that b is 4. I do believe that's correct, if I did not make any careless mistakes. Either way, it's the process that matters mostly, and hopefully my student understands that process. All right. Use implicit differentiation, looking here now. Find the equation of a tangent line to the curve at the given point. All right, I am just going to do this as quickly as possible with the assumption that my student is getting the hang of it. All right, so we're going to move through this quickly. I believe that's a 15. All right. And then we got the product rule right here. We will preserve the first thing, derivative of the second thing, change the first thing, keep the second thing. Looking here, yeah, looks like no real opportunities to simplify stuff. We've got to keep these terms on the left. Let's subtract away these guys. So on the next line, that would end up being this right here. It says 14y dy over dx. Pardon the handwriting. I know it's kind of getting bad. Negative 14x minus y, right? Because we subtracted that. Factoring out the dy over dx gives us x plus 14y, and that equals negative 14x minus y. Dividing both sides by x plus 14y would give us the final result. I'll stick the negative in front. We're going to have a positive 14x plus y up top, and then we're going to have an x plus 14y down below. Might seem like there is a temptation to simplify or cancel. These are not the same. Unfortunately, you cannot cancel anything there. But nonetheless, that's the derivative. Now, the point over here, I could see it's 1, 1. So we're going to get this over with right now. That would become 14 times 1 plus 1 all over 1 plus 14 times 1. Well, what do you know? That would be 15 over 15, also known as 1. The slope is 1. Okay, so we've got a slope of 1. We've got a point called 1 comma 1. This one's going to be a piece of cake. It's going to be y equals 1x plus b. 1 equals 1 plus b. B equals a big fat 0. So therefore y equals x. Believe it or not, after all that, y equals x. That is the equation of the tangent line of the curve at that given point. All right, looking at this problem, find dy over dx by implicit differentiation. All right, I'm going to assume that that's x over y, all right? So, pretty sure it is. So, number 9. E to the x over y equals 5x minus y. Okay, well, we're gonna take the derivative of the whole thing. Let's start with the easy stuff. All right. So, I'm a big fan of remaining in the flow when I do stuff. So, I start with the easy stuff. So, 5x becomes 5, and then we end up with, well, what's the friggin' derivative of y? Well, we know it's dy over dx. I mean, that's it. This e thing, keep in mind, if you have e to the x, well, the derivative of that is just e to the x. So, the derivative of this is just itself, right? Just itself. But it is a chain rule situation because we're not dealing with e to the x, we're dealing with e to the x over y. So we have to multiply this by the derivative of what I refer to as the mutant. The mutant is x over y. So now I think it's helpful to realize that x over y is really x times y to the negative 1. So that's a way of going about it. And the derivative of that, if we're going to do like implicit differentiation, would be a power rule. That's one way of doing it. So we'll keep the first thing. We'll do the derivative of the second thing. That's going to be negative y to the negative 2. But we're going to have to multiply that times dy over dx. So I'm going to have to give myself some more room. Make this a little nicer looking. So that's negative y to the negative 2 times dy over dx inside the parentheses, and then we're going to do the derivative of x times y to the negative 1. So simplified, that becomes, negative x over y squared times dy dx plus 1 over y. So that's just a ridiculous scenario. And this whole thing, since this is the derivative of that, this would go here. So we're going to have to find a way to squeeze that in there. I'm not going to try. I'm going to keep all of this visible to me. I'm going to keep all that visible to me as I just simply kind of do it on the next line. So we have e to the x over y times a big thing, and that's going to equal 5 minus dy over dx. Well, what goes in the big thing? That's going to be negative x over y squared dy over dx plus 1 over y. So let's see here. We will have to distribute, unfortunately, so we're going to distribute the e to the x over y, and that becomes negative e to the x over y times x over y squared times dy over dx plus e to the x over y because of the distribution of this to the 1 over y. That becomes this. And that whole thing equals 5 minus dy over dx. Now we still want the terms that have a dx in it to be isolated. I say we keep them on the left. So we're going to keep this here, and we're going to add this, and we're going to subtract that from both sides. So, in doing so, we end up with negative e to the x over y times x over y squared times dy over dx plus dy over dx equals 5 minus e to the x over y all over y. And then factoring out the dy dx on the left would give us negative e to the x over y times x over y squared plus 1. And that still equals 5 minus e to the x over y all over y. Dividing both sides by this gives us the final result of 5 minus e to the x over y itself over y all over negative e to the x over y times x over y squared, keep these in parentheses, plus 1. Now, that might be sufficient, but you could always also take out the negative, and we still have this up top. But the signs down below would change. Just going to keep these in parentheses to keep them separate and organized. I also want to make clear that this is an exponent, you know. Minus 1. So unless I made a careless mistake here, that is the derivative. Now, what are they asking for here? Just the derivative. So I do believe that's it. Okay, I do believe that's it. Again, it's the process that's important, not so much whether or not I made careless mistakes. You could always root those out later, obviously. All right, so that's that one. Alrighty, and finally we have another implicit differentiation problem, number 10. That is 8x cubed plus x squared y minus x y cubed equals 6. Alright, I think this one's easy. After all that craziness, I think this one's actually easy. So 24x squared. Okay, well, this is definitely going to be a power rule, so that's a little bit annoying, but it's not nearly as bad as what we've had to deal with. We will have, I mean, the power rule applies to this guy. But then you have another power rule, you know, for this guy. So we will even keep the color there. And we know, you know, that whole thing is just going to equal 0. Okay, so we're going to keep the first thing, change the second thing. So y becomes dy over dx. And now we're going to change the first thing and keep the second thing. So that's that. Keep the first thing, change the second thing. Dy over dx in there. And then we're going to change the first thing, keep the second thing. Pretty sure we're on the right track. Just got to make sure we remember that the dy over dx is right there. Let's kind of look at this to see just right now if there's any opportunities for simplification. There are not. So I don't really mind leaving these in parentheses for now. As usual, taking note of the terms that have the dy dx in it, and it's those. So let's just get it in our head that we're going to keep this on the left, and we're going to subtract this, we're going to subtract that, we're going to subtract that. So keeping what we want to keep on the left gives us this. We'll put the 3 out front. And we end up with negative 24x squared minus 2xy minus y cubed. All right, factoring out the dy over dx would give us this. And we have this remaining on the right, dividing both sides by x squared plus 3xy squared would isolate the dy over dx, which is good. I'm going to negativize the entire fraction, which means changing the sign of the numerator terms. And down below we have what we divided by. Feel pretty good about that one. That one was, I'd say, significantly easier. All right. So that is that one. I hope my student understands that, all right? So feel free to ask questions below if need be in the comments. And good luck to you guys. Good luck to my student. And I will talk to you later. Bye.